so we're going to finish up 11.2. And it wasn't yesterday, but last time we had class where we learned something new, we talked about adding up terms in a finite series. Well, we're going to look at how we could add up terms in an infinite series. So whether or not you can add up infinitely many numbers and get an answer depends on the numbers you're adding. Sometimes you can, sometimes you cannot. And basically what ends up happening is you can add up infinitely many numbers and get an answer as long as what you're adding each time is getting smaller and smaller and smaller. So like if you took a sequence like 10, 5, 5 halves, 5 fourths, what am I doing each time? Yeah, taking half. Yeah. So eventually, if you keep taking half of a number, by the time you do that 10 or 20 times, the number that you're adding is getting so small, it doesn't make a difference anymore, essentially. So that's going to be the key, whether or not we can add up infinitely many numbers.
It has to be decreasing.
It has to be, the value in the sequence has to be approaching 0. Because I can write a sequence that's decreasing that would not add up to anything. For example, this sequence. If I continue that sequence forever, eventually it's going to start becoming negative. It's still decreasing, but the value of the terms is not approaching 0. It's approaching negative infinity. So when you have an arithmetic sequence, you can never add up infinitely many terms in an arithmetic sequence and get an answer. That's not infinity or negative infinity. It can only work in a geometric sequence where the common ratio is less than 1 and bigger than 0. It has to be between those two values. Okay, so first of all, what would the notation look like? Well, when we use sigma notation, we have usually a number at the top. But now, instead of having a number, we have the infinity symbol. Okay, so that's how you'll know you're adding up infinitely many terms, if it's sigma notation. And then if they wrote it in expanded notation, you would have a ... at the end. This is what it looked like last week. It had a definitive stopping point. You might not have known where the stopping point was, but it did stop somewhere. Well, now, it has ... at the end, which means it just keeps going. Okay, so that's the notation for an infinite summation. Infinite series. Now, we can't really add up an infinite number of terms by hand. Right? That's not possible. So instead of adding up infinitely many terms by hand, we're going to actually see what does it look like is happening if we were to add up infinitely many terms. Like maybe we just look at the first 10. And if we can see like, all right, the first 10 are adding up to 2.99999. Well, then that probably means if you added up infinitely many, it would be 3. So it's more like a limit. We're looking at what we're getting close to. And we'll use that formula that we talked about right at the beginning of class today, the formula for a finite geometric series. We can use that to figure out the formula for the infinite series. And a lot of times you might think, well, adding up infinitely many terms is going to be a more complicated formula than only adding up a certain amount. And it's not true. The infinite formula is simpler than the one we just went over before we started the video. There's a lot less stuff in it. So the idea is, if you want to kind of visualize what we're going to do graphically, imagine that you added up certain sums, right? If you had something like, let's take 10 5, 2.5. And let's just use those. And let's say we wanted to try to predict what would add up, what it would add up to if we did infinitely many. Well, if we took a piece of graph paper, let's take this one, and let's put my axes like way down there. If I add up the first one terms in that sequence, what do I get? 10. 10. So 1, 10. What if I add up the first two terms? 15. I get 15. So 2, 11, 12, 13, 14, 15. What about the first three terms? 17. So we get 17, 1, 2, 3, 15, 16, 17.5. What's going to start happening is if we keep, and then what would the next one be? 1.25. So that was what? 17.5 plus 1. 18.75. So 18.75. So that's 17, 18. So now, I think that was right. 17.5, 18.75. So what's going to happen is the sums are going to start to approach an asymptote. We don't necessarily know what that is in this case. Maybe it's 20. Could be. I think it is. But the idea is it's going to be some line up here that as you keep adding more and more sums, it's going to start to basically go like this. And it's going to be getting closer and closer and closer to that dotted line, but never reaching. And that's what I'm going to try to describe in words right now, what I just showed you right there. So, let's pretend that there was some number that you could do y equals that number and draw a horizontal line. And that horizontal line was an asymptote for the sequence of partial sums. Right? So this would be like S1, sum of the first one, sum of the first two, first three, first four, and so on. And as you graph all your partial sums, they start to get closer and closer and closer to that horizontal asymptote. Then what we can say is that your partial sums are starting to converge. What are they converging to? They're converging to whatever that horizontal line is. In our case, I think it might be 20. In fact, if I posit it's 20, I could prove it's 20 using the formula. Okay, so your partial sums are starting to converge to the horizontal line, and when they start converging to it, that gives you an idea of what would happen if you did this forever. Because we can't do it forever, but we can start to look at the pattern. And you're looking at the pattern of your partial sums as you head to the right. What are they starting to get closer and closer to? If they're not getting closer and closer to anything, then we would say that our series is divergent. For example, if you added up numbers that doubled each time, 2 plus 4 plus 8 plus 16, that's not going to approach anything. It's just going to get bigger and bigger and bigger and bigger.
Is that not approaching infinity?
Well, if it goes to infinity, then we say it diverges. To converge, it has to approach a number, not infinity.
Yeah.
It has to approach an actual, like, real number. And that number that it's approaching is considered the sum of the series. Now, graphing it and visualizing it that way is fine. Eventually, we want a way to do it without graphing it and looking at the dots. And I'll show you the formula that we can use. Okay, so the more and more terms that you add up, the closer and closer your partial sum is approaching the infinite sum. And I would say generally, if you add up the first 9 or 10, that's going to be enough to know. I mean, even if you just look at our problem, by the time we added up the first 5 terms, we were already at 18.75. Maybe you could add up the 6th or the 7th one and get you up to 19 point something, but you're going to start to see it's not going over 20. So any question on that idea? Looking at those partial sums approaching an asymptote. Yeah.
Is the asymptote always an integer? Oh, is it?
No, it doesn't have to be. No, it could be a decimal. Like let's say I started off with the number 5.5, and I took 1/3 of that number each time. It would add up to a sub 1 over 1 minus r. So whatever 5.5 divided by 2/3 is, it's probably not an integer. I don't think it would be. So yeah, you can add up to a decimal. And I'm going to show you what I just did here in a little bit. All right, so technically an infinite series isn't really a sum of infinitely many things, because that's impossible to do. But it's looking at a pattern of partial sums. We're just going to look at the pattern really far down. And technically it's not even that far down, maybe the first 9 or 10. But that's what I mean by looking at the pattern further out. You can't really graph partial sums on the calculator, because if you tried to graph, or even if you came up with a formula for those dots, the calculator is going to connect them. And when you're talking about partial sums, it wouldn't make sense to have like something between S2 and S3. You can't do that. So I don't think there's a way to visualize it on the calculator itself. You'd have to write like a program that would plot points instead of connecting points. All right, so here's our notation specifically for a geometric series. This is what it would look like if you were to write it out as a sigma, in sigma notation. So remember, each time you start with a term, and then you're going to multiply by the r value. So if we look at an example, let's say we started with 6. And each time, we multiplied by 2. What's the first term in the sequence that I'm describing? Right here. 6. How many times did you multiply by r to get this number? How many times did you multiply by r to get the first term in the sequence?
You did.
You did. So technically it's like there's no r value there at all. Now the second one, you would have 6 times what? How would you get your next term?
Right, sorry, how did we get those numbers there?
The 6 and the 2?
Yeah.
It is made them up.
You multiply, you have 1r, so that's 2.
Right. So in this one, you end up multiplying by 2 for the first time. And then to get the next one, you'd multiply this by 2 again. So that's why this one would be r squared. And then the next term after that, you'd be multiplying by r another time. Notice, if this is your position number, how does the position number compare to the exponent on r?
One higher.
Yeah, the position number is 1 higher. You could say the exponent is 1 lower. That's why that has an n minus 1 there.
Yeah.
Because the position that you're at is always 1 higher than that exponent. Because you don't have an r at all on the first one. So that's where that n minus 1 comes from. So then if you wanted to know what the 30th term is going to be, how many times would you have multiplied by r to get to the 30th term? 29 times. So it would be 2 to the 29th power times 6. Okay, so just try to explain those exponents on the r's a little bit. So technically, if you want, you could put in an r to the 0 here, r to the 1, and so on. All right, now, I haven't really shown you the formula for doing an infinite series yet. But let's just use the formula that we already know for finite. And let's just say we add up the first 6. I think if we do that, it's going to get us close enough. Right? So we'll kind of make a chart and imagine like we're going to graph those partial sums and see what they're getting close to. Now, let's just write down what the formula is. I already went through the formula, so we didn't have to do it. But can someone remind me, what's the formula for adding up just the first n terms in a geometric series?
So the A1 times the numerator was 1 minus r squared. N. R to the power of n over 1 minus r.
Yeah. And I've already done this out. I think I did it for 4, 5, and 6. So we can see what we get. But before I show you what I got, what's the first term that we're using here? 2. If you forget where the first term is, it's always the net value in front of the r. Or you can plug in 1 for k and figure out the first term now. But you're going to get 2. So first term is 2. And what's my common ratio? 1/3. Okay, I'm multiplying by 1/3 each time. So let me fill in 2 for a sub 1 and 1/3 for r. And that's what you get if you add up the first 4 terms. 2 times 1 minus 1/3 to the 4th divided by 1 minus 1/3. Now, I'd say if you look at the first 4 terms, you can probably figure out what this is adding up to. What do you think it's adding up to? 3. Yeah. If you do the first 5, I think that kind of confirms it. So fill in your r value, fill in your first term, and you'll do that out, you'll get about 2.9877. If you add up the first 6 terms, you get 2.9959. So it's getting very, very, very close. So if we were to add up infinitely many terms, what would you think it would add up to? Yeah?
Yeah, it really may be.
Yeah, it would add up to 3. Or it would approach 3. It would get as close as you want to get to 3. Technically, it never reaches 3 because you can't add up infinitely many things. But if you could, it would hit 3. Now, another way you can get these values quick so you don't have to type them in each time is put this in a formula. So that way when we type it in, we can use the table to get these partial terms. So let me show you how to do that. It's just a little messy to type in because you've got some fractions. But here's how you can do it. So we've got 2, and then in parentheses, let's do another parenthesis, 1 minus 1/3 to the x, and then close the parenthesis because you're done with the numerator, divided by, and it's easier to just do 1 minus 1/3. What is 1 minus 1/3? 2/3. Close your denominator, and then close from when we open the 2 in front, and I think I did everything correct. Oh, let's check. So if we go to our table, let's put in, oops, I need to put in the values, 4, 5, and 6. Okay, and are those the decimals that we got? Yep. I would say by the time you even get to like 11 or 12, it's probably just going to say 3 because it's going to run out of decimals. You might be able to highlight it and you can still see that it's not quite 3. But even that, once you get to probably the first even 25 terms, now it just says 3. So you really don't have to look that far to add up infinitely many numbers. They converge usually pretty quick. Okay, so any questions on how we got those numbers? Okay, so how would I write the answer? I would say sum of the series is converging to 3. The sum of this series is converging to 3. The closer that number is to 0, the faster it converges. If you take 1/3 of a number each time, that gets pretty small pretty quick. But if I take 1/100th of a number every time, that's just like converging like off a cliff. It just converges real fast. And then if I were to take like, say, 99/100ths of a number each time, well, that's going to converge extremely slow. Because it's like you're taking like 99% of the number each time. So it gets smaller, but it takes a while. All right, so we already kind of did the visual. I can hit graph if you want to see it. Let's see. It doesn't make sense to look at negatives. Let's set our y max at like 4. And you don't really want to visualize this as being connected. You would want to visualize it as dots. But look how fast it converges. So here's S1 right about there, S2 right about there, and then S3 somewhere there, and then S4. I think S4 was already pretty close to like 2.9 or something. But those are my partial sums. All right, so to visualize that sum, this is how you graph it on the calculator. That's exactly the formula I typed in. If you want to see it, I can put that up so you can see it. That was the formula. And remember, when you look at your table or look at the picture, focus on the positive integer values for x. Doesn't make sense to look at anything in between. There's nothing. So as you let this number get bigger and bigger, in our case, I'd say let it be 6. It's high enough. Even really 4 or 5, and you could tell. That's a good approximation of what's happening to your series. Now, I think I'm going to look at this at some point, but this is a good place to look at it. I said to you that when you graph something that's geometric, it will only converge if r is a certain value. What did I say r had to be between?
0, 1.
It has to be between 0 and 1. We can look at what happens if r is not between 0 and 1. So we already did this, so I'm not going to go through this problem again. But I'll do it with 1 that's not between 0 and 1. So this time, what's my r value here? 3. And what's my first term? 4. So let's change the first term to a 4. And let's just make r 3. In the bottom, I'm trying to think, that would be 1 minus r. So what would be in the bottom? Negative 2. So that's 1 minus r to the n over 1 minus r. And I've got some extra parentheses. I only have them in there because of the problem I did before. That's fine. Okay, so what if you let k equal 1? What's your first term?
0. No, it's just, yeah, it's 1 minus 1, so the exponent is 0.
Your exponent is 0, yeah? 4.
So it's 4 times 0, isn't it?
What's 3 to the 0?
0. No, it's just 1.
1.
Anything to 0 is 1. What's 3 to the 1?
3. That's the next
Oh, yeah.
3 to the 1 is going to be the next
Yeah.
one, because now plug in a 2. 2 minus 1 is 1. 3 to the 1 is 3. And 3 times 4 is 12. So what happens is you're multiplying by 3 each time. Right? We can check our table and see what happens if we add up the first 1 terms. We get 4. What if we add up the first 2? What should I get? 16. And I do. And what if I add up the first 3? 52. So that's going to be 16 plus 36, which is 52. So look at what's happening as we add up more and more terms. Yeah, it's just getting bigger and bigger, and it isn't approaching any value. So this is an example where the sum is diverging. Okay, it's not adding up to anything. So as x gets bigger and bigger, we can look at the graph. All you're going to see here is it's going to curve like exponentially right off the screen. It curves so fast you can't even tell. So I'd probably have to set the window up to like 10,000 so you can start to see a little more of a curve. We can try it. But even that, it's still going to curve off the screen really fast. So by the time you get to like the 7th or 8th value, it's already above 10,000. There's no horizontal asymptote here as you head to the right. That's the point. Okay, your dots are not getting closer and closer to anything. So we would say that this series diverges. So sometimes a geometric series will converge, sometimes it'll diverge. It depends on the R value. So in the book, I think they had something next where you could like practice on the graphing calculator, putting in different values for R, and then seeing what happens. But I think if we just look at the R value, I don't think you need to graph it to figure it out. So there's your formula for the sum of a finite geometric sequence. And if you plugged in 0.8 for R, do you think that would cause it to converge or diverge? Yeah, this would converge. Because what you're getting each time is a number that's smaller than the one that came before. How much smaller? 0.8 times 0.8. So it's only 80% as big as it was the previous number. How about B? That would converge. How would the rate of convergence compare to the one above it? Faster or slower? Slower. Because if you take 90% of a number each time, it's still going to get smaller. But not as fast as if you take 80%, or even if you took half a number each time. It gets smaller faster.
Typically, aren't you taking like 0.2, not 8, because you're subtracting from 1?
Well, the R value leaves you with 80% of the number you had before. So like if your first term was 10, your next term is 8. And then your next term after that would be 6.4. So that number is 80% of that number, and so on. I think that's right. How about if R was 1.1? That would diverge. Yep. So that would diverge. And what about 1.2? And which one would diverge faster? Yeah, this is going to cause your number to get bigger faster because you're multiplying by a little bit bigger value. Now, when we talk about converge and diverge, we have to be a little bit careful whether the question is asking about is the, well, let me write out. Let's say we had 10 fives when we did before. 5 halves, 5 fourths, 5 eighths, 5 sixteenths. Now, let's say I asked you what the terms in that sequence are approaching, or what the terms in the sequence are converging to. Can anyone tell me what that would be?
5 over 10.
Which is getting closer to what number? 0, yes. The terms in this sequence are approaching 0. Now, what if I asked you about the sum of the terms in the sequence? What did we say these were approaching? 20. So there's a difference between those two questions. What the terms in the sequence are converging to, or the sum of the terms in the sequence. Just make sure you read which one they want to know. All right, so after kind of exploring those different R values, you can see that anytime the R value, technically it could be negative. I did say between 0 and 1, but it could be anything between -1 and 1 except 0. Because even if you multiply a number by, let's say, -0.5 each time. So let's take like 50 multiplied by -0.5. Okay, so you get -25, and then multiply that by -1, -0.5. Then you get +12.5, -6.25, +3. So what's happening here is you still have an asymptote, but your terms are kind of oscillating around it like this. They're going above and below it, but they are closing in on 0. Is there any question on that? So you can multiply by a negative number, and that is still considered convergent. Even though it's oscillating up and down, it's closing in on a value. So let's see if we can figure out what the formula is for an infinite geometric series. Okay, here's the finite one. If we wanted to look at this for an infinite series, essentially we have to let n approach 1. Yeah, so let's let n approach infinity. Now, we just learned that it only converges for what kind of R values?
Converges for ones that are smaller than 1.
Smaller than 1 and greater than
0.
Greater than 1, but it can't be 0.
Yeah. So, because if it was 0, then, well, you'd be multiplying by 0 each time, and then your terms would just be zeros. So generally, when we talk about converging or diverging, it's a number between -1 and 1, but not 0. So think about what would happen here. If R was a decimal that converged, okay, just pick any, 0.5. If you took 0.5, or any number that's between -1 and 1, and raise it to an extremely high power. Power in the millions.
Really, really, really small.
This starts to get really, 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 really small. And what does that thing that I circled approach? It approaches 0. Right? Take 0.5 and raise it to the 100th power. It's basically 0. So as n approaches infinity, this basically doesn't matter. We don't need it because it turns into 0. So if that turned into 0, what would that leave me with for a formula?
Just 1 over 1.
Something else too.
Oh, A, the first term.
The first term times 1 over 1 minus r. And now, what if you put all that together?
A1
Mhm.
over 1 minus r.
Yeah. And that is the formula for the sum of an infinite geometric series. Keep writing that, sorry. It doesn't need this r to the n anymore because it basically approaches 0 as n gets bigger and bigger and bigger. So let me write that down right here. Well, I'll write it again. Okay, so as n approaches infinity, we get a sub 1 over 1 minus r. Now, you can use that formula if you want when that condition doesn't work, but it doesn't mean it. So this formula only really has meaning when the r value is between -1 and 1. If you use it other than that, I don't know what it's telling you. It's not telling you anything. So any question on that one? So this is the sum of an infinite geometric series. And it is a simpler formula than a final. It has a lot less in it. All right, so now that's the way to go if we have to find a sum. We don't really want to graph it and look at an asymptote, see what things are getting close to. We also don't want to have to do like a table, like I did. Was it right here? Yeah. We don't want to look at like what happens if you add up the first 4, then the first 5, and the first 6. Why don't we just jump right to what the result will be using that one? Right. So, first of all, on this one, we have to figure out if it would even converge. And if it doesn't, then we just say it diverges and there is no sum. This does converge. How come?
Because your r is 1/2.
Right. So what's the first term if you were going to generate the terms in this summation? The first one is
It's
5, and then the next one?
5.
5 halves, then 5 fourths, 5 eighths, 5 sixteenths, taking half each time. So the terms themselves are approaching what number?
0.
0. Now we're going to figure out what the sum of the terms are approaching. Okay. What's the formula that we just came up with?
A1 over 1 minus r.
A1 over 1 minus r. So that's A1 divided by 1/2.
Which is 10.
So 5 divided by half is 10. So if you were to add up all the terms in this summation to infinity, it would approach 10. And if you actually could go all the way to infinity, it would be 10. And that's how you find the sum of an infinite geometric series. Okay. Any question on that? That was 11.2, part 2.
Pretty quick.
So tomorrow we'll do 11.3 which is a little different, and then we'll do 11-6 on Wednesday. Okay, so that's homework for tonight. You've got a little under 30 minutes left.
Yeah.
So you could use that time to try to get some of that done. If you need to make up any tests, I'll be here Thursday after school, or Thursday during class is a review day. So you could also do it then.
No.